All right, so next concept we'll be taking a look at is heating curves. So let's think about this kind of logically. When you heat something, the temperature goes up. Right, pretty logical statement, but let's see, let's put this here in these quotations, or does it, or parentheses, or does it? So let's go ahead and do a little thought experiment. So you're gonna put a water on the stove, a pot of water on the stove, and then you're gonna boil it. So you boil some water. And then of course, water boils at least at sea level at 100 degrees Celsius. So it's a 100 degrees Celsius and the water is boiling. And then you leave that there for, let's say, like half an hour. You're gonna leave it on that stove with that stove on, so you're adding more heat. And then you take the temperature of that boiling water. When you do so, what you'll find is that the temperature is still 100 degrees Celsius. So it was 100 degrees Celsius, you added more energy into the system, and it's still 100 degrees Celsius. And remember, energy can't just be destroyed, so it's got to be going somewhere. So where is that energy going? It's going into breaking these intermolecular forces to allow your phase transition to occur, right? So in a liquid, we've got our intermolecular force that's keeping these particles together. And then when we add energy into this system, we break that into a gas and we break those intermolecular forces. So the temperature of the system is not going up. The energy is all going towards breaking these intermolecular forces. And so let's just draw a plot of that. On the left side here on our y-axis, we're going to have temperature. On the x-axis, we're going to have heat added. And as we go from left to right, we're going to add more and more heat. So at first, when we start heating something, it's going to increase in temperature. And then we're going to say that it's a solid right now. So we're going to start off maybe with some ice, right? You start heating some ice and it starts warming up. And as you add heat, the temperature goes up, right? That's what this graph part is showing. And then eventually the ice starts melting. And same thing where how the water, when boiling, it's not changing temperature. Ice, when it's melting, it's not actually changing temperature. All that energy is going into breaking these intermolecular forces. So what we have is we have heat added, but no increase in temperature. So we get a flat line in the curve. And what's occurring here is a solid is being transformed into a liquid. Then once all of it is transformed into liquid, we can then continue to heat the liquid, right? So maybe at this point it's water, right? And then you start heating that water and that temperature will increase. And then eventually you're going to hit that boiling point. And again, the energy, instead of increasing the temperature of the liquid, is going to go into breaking the intermolecular forces. So what's going to happen is we're going to add heat, but we'll see no increase in temperature. And that's because here we have a liquid being transformed into a gas. And again, the energy is going into breaking these intermolecular forces. And then once it's all turned into gas, assuming you had some kind of, closed container, you could continue to heat that gas up further, right? So in this case, if you're taking the water analogy, it'd be steam. You can heat steam way above 100 degrees Celsius. So this is generally what a heating curve looks like. And the main thing that we want to say, and the main thing we want to extrapolate from this heating curve is that during phase transitions, the temperature stays the same. The energy that's added is being used to break the intermolecular forces.